Today we're going to be talking about cluster analysis. Cluster analysis is a statistical procedure used to break down data sets into homogeneous groups. So it's really good for developing a typology or classification. It's useful for investigating useful conceptual schemes and for grouping. It's good. It can be used for hypothesis generation as well as hypothesis testing. So, and we'll get to the ways in which it can be useful for I/O, but for now, let's get started with the R functions. To begin, I started with installing these two packages. They're already installed, so I'm just going to bring them all in using the library. We have ggplot2 for graphics, tidyverse for data manipulation, cluster for the clustering algorithms, and then facto extra is also going to help with those clustering algorithms as well as some visualization. So I prefer to bring my data in this way. I've created a project for, oh, I'm in the wrong one. I've created a project for cluster analysis, and I'm going to use this file, employee absenteeism. I'm just going to click it, import data set, and we're going to get to view it, which I also really like and prefer than using the code. And so as you can see, this is a very large organization. It's got over 8,000 cases in this data set. It's broken up by 21 different departments. Each case is going to have the person's department, the person's age, their length of service, and the amount of hours that they were absent. So I'm going to import that. It pops up again. As you can see, it's freaking huge. So I had initially I did the entire clustering thing with this huge data set, and it was really messy and it didn't show much. So just for ease, I'm going to break it down to departments. Since there are 21, we'll have 21 cases, and I'm going to average those continuous variables for each department. So I'll show you that in a second, but for now I'm going to rename it to EA for employee absenteeism. And then we're going to look at it, same thing. We have 8,336 separate cases. So right here, I'm going to group by department name. And then it's still the same as of now, but it does show that we've got 21 groups, and that's new. So then we're going to create a new object called new EA, NEA for short, and it's going to summarize it and also it's going to create the mean for each of these, and then kind of like, I don't know if collapse it is the right way to say it, but into those 21 departments. And then also here, I really don't want these names here because they're not continuous. And I think since each case is going to be a department, I thought it would be nice if each case's row was named the department. So that's what I'm doing here. I'm removing row names, changing the row names to the variable department name. Then we're going to get rid of the missing data. And for purposes of clustering, we need to standardize all the continuous data. So it's going to standardize age, length of service, and absent hours. And that's helpful because in age and length of service, we're working with years, but absent hours, we're working with hours, obviously. So we want to get them all on the same playing field. So I'm going to scale them. And now we can take a look. My final DF data frame. As you can see, these are now the row names. We've cut it down to 21. You can't see them, or maybe you can. I don't know if it's all 21. But yeah, and then we've got these standard numbers rather than the hours and days we're using. It's basically like a z-score for each one, or it is a z-score. So I decided that we're going to look at this at the end and just basically go through just the k-means cluster analysis for now. I had started with hierarchical clustering, but I'm not as for sure on that as I am with this, and I just want to prove that for the most part I know what's going on with this, and I can in fact conduct a cluster analysis, and we'll look at the hierarchical one after, but I just want to get through it doing the k-means. So to start, we really want to estimate the optimal number of clusters. So first we're going to look at compute the SCAP statistic, and it's basically going to data frame the function k-means, that's what we're using. In start, I set at 20 throughout this, and it just basically means that R is going to try 20 different random starting assignments and then select the best results corresponding to the lowest within cluster variation. It's just going to show me the top 10, and it's going to do like 50 variations of this. This is a bootstrapping, how many times it's going to create those sets. So going to run this, and it's going to load, which is kind of cute. Then we're going to print it out. And visualize it. And this is showing us that 3 clusters is optimal. So that is pretty cool. So we can do our k-means cluster analysis with 3. So gonna move on, create an object called k3 for k-means 3 clusters. We're gonna use our data frame. It's gonna have 3 clusters, meaning 3 centers, and then, like I said earlier, the end start's gonna be 20. So I will run that object, and we can kind of look at the structure of it. It's going to show us a lot of different things, like the names, where the centers are for 1 through 3, and then it's going to show us the names of the groups, which is length, and then our variables. We have our total sum of squares, which is 60 within sum of squares, corresponding with the 3 groups, 4.06, 2.04, and 7.13. The total within sum of squares is 13.2, between sum of squares 46.8. The size of each group, which is 8, 5, and 8, iteration 2, and then I fault. Which is a component I am not very familiar with, but I'm not, it's 0, so I'm not quite sure how important it is. So I'm going to run this kviz cluster. It's going to run this object with my data frame and create it, and then let's look at it. So as you can see, we've got 3 clusters here, and they seem to be pretty distinct from each other, so it looks like the clustering was pretty successful. You know, we've got this first one that's high on this dimension but low on this one, one that's mid to low on this dimension, and middle on this dimension, and then high in both are all dimensions over here. And we also see these bigger dots in the center, which are the centroids. We're going to talk a little bit more about the center, so I'm going to go back and run this. Got it here twice now. But since we just have these dimensions on the sides and it's not saying exactly what the variables are, it's nice to kind of look at this because we can see that group 1 is approximately, they're on the lower end of length of service, the higher end of absent hours, and the lower end of age. So that's our first one right here. We've got this number 2 cluster, the blue one, which is pretty high on length of service. In the middle on absent hours, and really high on age. Then we have 3. Oh, that was the green one. My bad. That was for the green one. The green one's number 2. That makes way more sense. The third one is this blue one in the middle, which is in the middle on length of service, which makes sense. Low on absent hours, and pretty low on age as well. So as you can see, we've got 3 clusters here. And they seem to be pretty distinct from each other, so it looks like the clustering was pretty successful. We've got this first one that's high on this dimension but low on this one, one that's mid to low on this dimension, and middle on this dimension, and then high in both are all dimensions over here. And we also see these bigger dots in the center, which are the centroids. We're going to talk a little bit more about the center, so I'm going to go back and run this. Got it here twice now. But since we just have these dimensions on the sides and it's not saying exactly what the variables are, it's nice to kind of look at this because we can see that group 1 is approximately, they're on the lower end of length of service, the higher end of absent hours, and the lower end of age. So that's our first one right here. We've got this number 2 cluster, the blue one, which is pretty high on length of service. In the middle on absent hours, and really high on age. Then we have 3. Oh, that was the green one. My bad. That was for the green one. The green one's number 2. That makes way more sense. The third one is this blue one in the middle, which is in the middle on length of service, which makes sense. Low on absent hours, and pretty low on age as well. So in regard to I/O, this could be really helpful for this organization, because if they're really interested in seeing like the groups that are the exact classifications, maybe not exact, but the general classifications based on age and length of service, if they ever wanted that for whatever reason, they might have better continuous variables to look at. But for now, this is what we're working with, and so they could see, the group, the first group, it was really high in absent hours, but they're also on the lower end of length of service and age, so they haven't been there long enough. Maybe they're, not committed to the organization, and they're really young, so maybe they're just goofy. I don't know. In contrast, we have this group that's a lot lower in absent hours, and they're the highest length of service. They've been there the longest, and they're young, but not quite as young as this group. So it's just an interesting bit to look at. Like I said, the more variables that you have, sorry, my dog is running around. I don't know if you can hear that. The more variables you have, the more information it can give you, and you can start, um, implementing interventions for, say, this group to figure out why, they're missing so much work and start implementing those interventions that might improve that. I have for k-means, I do kind of want to play with this hierarchical clustering just to show you that I tried. And I have a pretty good grip of it, just not quite as good as the k-means. So let's head down here. I'm thinking, or from what I understand, you have to run or figure out the Euclidean distance. I'm going to name this object D for distance, use my data set, my df, and then this is the method I'm using, and then we're going to print it. And it kind of creates this matrix. I wish it were prettier, but just pretend like it is like a full matrix, a 21 by 21 matrix, where they are kind of giving a closeness, or it's not closeness, similarity score. So like, for example, this 0.03 right here between employee records and service, they're going to be pretty dissimilar compared to this accounts receivable and training across our different variables. So that's pretty neat. I also understand that hierarchical clustering kind of starts from the bottom up. I'm going to go ahead and run these. I'm using the method ward. I'm using my D object, these distances, and this is the HClus standing for hierarchical clustering, and I'm going to name it fit, and then we're going to plot it, and it's going to show a dendrogram, and we can kind of look at that right here. So yeah, hierarchical clustering, it starts from the bottom up, and it shows sorry, and it shows each of the departments, and it's going to cluster it piece by piece with whatever's most similar to it, and it's going to create this tree-like graphic. And as you can see, we're kind of at 3 clusters again, so this, I can kind of show that. I'm going to call it groups. It's going to cut the tree, this object fit, and then K3, it's going to cut it to 3 clusters. So I ran that, and then it's just going to redraw this, but with these little groupings around it, so it's showing us our 3 clusters. There's also a silhouette plot that is going to cut into 3, and from what I understand here, it runs on a scale of -1 to 1, 1 being how well that case belongs in that group. So this is group 1, these 9, and then these 6, and these 6. And like, this is showing that 20 really does not fit very well in group 1, same with 13 in group 3, but like all of group 2 seems to fit extremely well into that group. So it's just another way to look at your groups and their fit. We also have the scree plot that's going to show the within sum of squares. This is where I get a little bit lost. I'm not quite sure what's going on here. Plus, I think it needs to be working with. No, I think that's right. Okay. And gonna plot that. I do know, I understand this chart. It's the code I'm still working with, but it's got the within group sum of squares and the number of clusters. And it ran 20 random clusters, or not random, it ran 20 clusters. And then basically these three are the best because you want there to be more bigger differences in sum of squares between them to show that they're, you know, distinct from each other. So these are too close for us. We're not really wanting that. So this is just another way of showing that we want these first three number of clusters. And that is kind of all I have for hierarchical clustering. I hope I explained it in a way that made sense, and it's catching on with me, but yeah, that's all I got. I will see you next time in LPA/LCA.